Hello everyone. So today we are going to discuss different modulation schemes which will be used in optical wireless communication systems. Now in systems which are based on light, for example visible light system, normally they use LED or laser as the source, and these source they require positive signal and real signals. This is different from what we have in RF, where the signal could be bipolar, positive as well as negative, and also signal can be complex. It has both real parts and imaginary parts. So for optical wireless systems, there are some specific modulation techniques which are used. Not all RF techniques which have been used are directly can be used in optical wireless systems. There may be some modification required. Some of the advantage we have in RF scheme using a particular modulation scheme, those advantages may not be there in optical wireless communication systems. So we need to understand the modulation schemes which are specifically useful for optical wireless communication systems. So before we start the discussion on modulation schemes, we want that the power either from the transmitter or from the handheld device using optical wireless technology should be as low as possible. So you should look for modulation schemes which is power efficient. And also we know the bandwidth offered by different sources also limited. The optical wireless channel bandwidth is also limited. There may be huge bandwidth available in the spectrum, visible spectrum or IR spectrum, but it is limited by the bandwidth of the devices. So we need to have a modulation scheme which is bandwidth efficient. So before we start, let us understand the different parameters which we will try to calculate for different modulation schemes. For example, power efficiency. So the power efficiency is average optical power required to achieve a certain BER. So this is average power required to achieve certain BER. This is how we define the power efficiency. And for power efficiency, there is a term which is called eta power efficiency, which is defined as E pulse, that is energy in the pulse, and energy in the bit, or average energy per bit. Average energy per bit. This is energy in the pulse. This is how we define. So for different modulation schemes, we will calculate this power efficiency parameter. The other important parameter which is to be discussed or which is to be calculated for different modulation schemes is bandwidth efficiency. Now, bandwidth efficiency is defined as eta B is RB, that is achievable bit rate, divided by the bandwidth of the transmitter or receiver. So this is bandwidth of transmitter receiver, and this is the achievable bit rate. And the units are bits per second per hertz. So we need to calculate these two important parameters for any modulation scheme, the power efficiency and bandwidth efficiency. And in VLC, for example, I'm taking one of the optical wireless communication technology, that is visible light communication. Normally we use intensity modulation direct detection. So you modulate the intensity, that is whenever there is a logical 1, the device is lighted, whether it is LED or laser, you get light here. And whenever there is a 0, this device is off. So this is called as intensity modulation. You are modulating the intensity. And signal to the laser diode has to be real and positive. So if I'm trying to use some RF signal, which generally is bipolar and complex, I cannot directly give it to the LED transmitter or laser transmitter. I'll have to modify that signal to make it real and positive. So under this modulation schemes, we will discuss about some baseband modulation techniques such as pulse amplitude modulation, pulse position modulation, pulse interval modulation, and also we will discuss about variable pulse position modulation. So, and also subsequently we will discuss the multi-carrier modulation like OFDM, and also we will discuss about color shift keying. This is another modulation scheme which is used in optical wireless communication systems. So we will try to analyze, understand these modulation techniques, try to calculate BER for each one of them, and also see which one of them are power efficient, which are bandwidth efficient, and also we can use OFDM. It has to be modified to suit our optical wireless requirement. So we will study all these modulation schemes one by one. So before going into the modulation, let us try to understand two types of signaling, which is NRZ signal and RZ signaling. So in NRZ signal, you have one which is denoted as, this is 1, this is duration of the bit, and this is some power P. And for 0, this is TB, there is no power. So this is NRZ signaling. And for RZ, that is written to 0. For half of the duration in 1, pulse is high. So this is RZ. So this is logical 1, for example, and this is TB by 2, and then you have TB here. So this is how RZ signaling look like, and for 0, it is same. So this is TB. So there is no power at 0. So that's the difference between NRZ and RZ, which we'll be using when we discuss these different modulation schemes. And also let me tell you what is the power spectral density for NRZ and RZ. So for example, if I plot the normalized power on this side, normalized power, and this side is, say, normalized frequency. So for NRZ, this is the power spectral density for NRZ. So this is, you can say, on-off keying NRZ, OK, on-off keying NRZ. And for on-off keying RZ, I'm drawing with a dash, and this will be 0 here. So this is on-off keying RZ. So the first 0 occurs here for OK and RZ somewhere here, and for OK RZ, which require higher bandwidth, The first 0 occurs at point A. So this is a power spectral density for NRZ and RZ signaling. Now let us take a simple on-off keying system and try to calculate the BER for such a system. So as I mentioned, on-off keying is you have this is a digital pulse and you modulate your LED or laser diode. So whenever there is 1, the LED is forward biased and emits power. Whenever it is 0, there is no power coming. So basically you are getting on of the device and off of the device. There is an on-off keying. So we will try to calculate bit error rate for such a system. So the received signal, which is received after it has gone through the channel, optical wireless channel, the signal is actually, the received signal is Gaussian in nature. So let me draw how the spectral density of the received signal. So say, suppose this is the middle point and this is a logical 1. This follows Gaussian distribution. This is a logical 0. So logical 1 is, say, for example, here. Logical 0 is, say, somewhere here. And this will have distribution like this. This should go to 0 from and for logical 1 same, so it will go, that I am drawing with a dash. So this is also dash here. So let us call this as probability received signal when 1 was transmitted. So this is pi p y given 1 when 1 was transmitted, and this is the probability of received signal y when 0 was transmitted. And this is some sort of threshold I have put here. Let us call this as VTH. So anything, I don't know what this VTH, whether this will be in the middle or it is towards, towards 1 or towards 0. That depends, what is the probable PDF of the received signal for 1 and received signal 0. Because this can be different in optical communication systems depending upon the power and the short noise. So this is how this quantity is defined. So it is not necessarily that VTH will be exactly in the middle. It may be towards PY1, that we will see, or towards PY given 0. So right now I'm putting here. So the error component in this is, for example, this area, this is this area, the dash area is the error and the probability that I received 1 and when 0 was transmitted. So this is given by this dash area, and if you see this dotted area, which I am showing here as dots, is P, the probability that you got 0 when 1 was transmitted. And this is minus infinity, this is infinity. So we will try to calculate the BER for such a system. So if you see the probability that there is an error is given by this dotted area here, this one. And as you see, this is PY1, that is the probability, the received function when 1 was, the received signal when 1 was transmitted. And the limits are from minus infinity to infinity because this will extend to minus infinity. So this dotted area is the error part. So this is denoted by P1 VTH. And similarly for 0 VTH, that is P0 VTH, it is the dash area. The dash area is this here, somewhere here. So this goes from VTH to infinity all the way to the infinity here. So this dash area is the probability that in the 0, and P1 VTH is the probability in the 1. So we need to calculate these two areas. This is actually error in the system because I had transmitted 1 and received 0. In the other case, I had transmitted 0 and received 1. So I need to calculate these two areas, which will define the probability of the total probability of error or bit error rate. So the total probability of error will include both these areas, and A and B are the probability that 1 is coming and the B is the probability that 0 is coming. So for simplicity, we can assume the probability that 1 is coming is half, is same as 0. So A is equal to B is equal to half. The zeros and ones which are coming in the digital stream, they are in equal numbers. The probability of 0 occurring is half, probability of 1 occurring is half. So the total probability of error will be basically half P1 VTH plus half P0 VTH. And what is that VTH? What is that optimum VTH? Where I should put my threshold so that the BER is minimum. The idea is I want to have as low as BER. So what is the optimum VTH? If these two probability distribution functions are same, then the VTH will be exactly in the middle. But if these two are different, then it may not be in the middle. Because if you see in optical wireless system, there is something called short noise. And that depends on the input power or P received. So in case of 1, the power is high, the short noise is high. It may give different kind of probability distribution function. In case of 0, there is no power, there is no short noise. It can give you different PSD or power spectral density. So depending upon this, these two PSDs can be different, and also the VTH, the optimum threshold, is not in the middle. So let us try to calculate this optimum VTH. So as I mentioned, the dash area was P0 VTH. The units are from VTH to infinity. That is a error in 0. And this is given by this area. If you see this area, this particular area, the dash or the dotted area, depending upon what you consider. For example, if it is P1, it is dotted area. If it is P0, it is dash area. So I'm trying to calculate the 0. So it is from VTH to infinity, and the PSD of received signal when 0 was transmitted. And this can be equated as from VTH to infinity. This is Gaussian. This is how you calculate the area. If it is like this and you want to calculate this area, so it is represented in this equation where B of is the mean, that is this is B off, for example, and this has sigma variance for the off state, and similarly you have the B on average, B on, and this will be sigma square on. So this is for the 0, 1 by root 2 pi, 0 off case, the variance in the off, VTH to infinity, exponential minus the received signal V minus B of whole square divided by 2 sigma square of Similarly, we can write P1 VTH The limits will be from minus infinity to VTH. You can refer the same diagram which was there earlier. So the limits will be minus infinity to VTH, and here you have sigma on, that is the variance for the on state, and this is the average for the on state, and this is the variance, this is sigma on, this is root of variance. So this is the P1 VTH and this is the P0 VTH. So basically I have calculated both of these areas. So there are standard expressions for error function. So ERFU is defined as 2 root 2 pi 0 to u exponential minus z squared dz. And if you see, these expressions here, these two are of this form. If I slightly change, I can write in error function form. So doing this, and error function complementary is 1 minus error function u, which is given by same expression here. So the unit, the limits are changed. In case of error function, it is 0 to u, but when I say complementary function, the units are from u to infinity. So for example, this is 0 to u, and if I take 1 minus, then it becomes u to infinity, this part. So P0 VTH is given like this: VTH to infinity exponential V minus B of whole square divided by 2 sigma square of, and this can be written in the error function form as discussed earlier. So this in error function form is half 1 minus ERF VTH minus B of divided by root 2 sigma of. So this basically has come from this equation. So basically this and this, have been used to calculate the P0 VTH in the ERF form or error function form. And if you want to write in error complementary form, so this 1 minus ERF will be ERFC, 1 by 2 VTH is given by this expression. Similarly, I can calculate for P1 VTH. So P1 VTH on same, the way we have done for P0 VTH, half error function C. So this will be not VTH minus B off, it will be B on, the on part minus the threshold part, minus VTH divided by root 2 sigma on similar lines. So I have calculated P0 VTH, this area which is error in the system, and P1 VTH, again this is error for the 1 and this is error for the 0. So the total error will be summation of this and this, that area, both the shaded area as well as the dotted area. So that becomes the total error. So which is written as half A plus B, and A and B are as shown in the previous slide. So let us define a quantity which is there in this, that is VTH minus B off divided by sigma off, or B1 minus VTH divided by sigma on, as some quantity Q. So let us define this as Q. And from here I can calculate the VTH. So from these two I can calculate VTH, which is given as given here, sigma off into B on plus sigma on into B off divided by sigma off plus sigma on. And if I want that write that earlier expression in terms of Q, so the probability of error will be half error function Q by root 2 plus half error function Q by root 2. So basically I have replaced this Q in the earlier expression. So this is the probability of error in the form of Q. And so this can be added, and what finally we get, the probability of error as half error function complementary Q by root 2. And this can be written in the form of error function also. So 1 minus ERF q by root 2. Now let us assume that sigma off plus sigma on is sigma, some standard deviation, and this is actually and B on is some voltage V, this is the on voltage, and B off is 0. Then VTH will be in the middle because there are similar curve. Actually, this is not plus, this is equal. So the variance in sigma off and variance in on, they are equal to sigma, and B on is voltage V and it is 0 here. So if I put the value of VTH in the expression which had all these 4 quantities, I get VTH V by 2, that is exactly in the middle. So if my threshold is in the middle under these conditions, then the BR will be minimum. And Q, the factor using this is V by 2 sigma. And if I put this value of Q in the expression which I had calculated, so the BR will be 1 minus error function V by 2 root 2 sigma. And this is nothing but signal to noise ratio under root, because V is, if you take the V square, it gives you some sort of power, and if you take sigma square, it gives you the noise variance. So V by sigma is nothing but root SNR, 2 root 2 is coming because of this. So half 1 minus ERF root SNR 2 root by 2. Or it can be written in complementary form, half error complementary function root SNR 2 root 2. So this is the BER for a OOK system. So this is, let me write here, BER for on-off keying system. And this is, valid when I have these, the variance in the off and variance in the on, they are equal to sigma, and B on is defined by V and B off is divided by 0. If these values are different, then the earlier expression is valid where I had specifically written sigma off and sigma on. So if the variance for the off and variance for the on is different, then we'll have to use that equation. But if in case this is equal, and then your threshold where you have to put the threshold has to be V by 2, and the BR for such a system is half error complementary function root SNR divided by 2 root 2. So this was for OOK scheme. Now let us try to calculate BR for a M-ary PAM system. So M-ary PAM system basically consists of, so I'm taking a very general case. Normally, as I mentioned you earlier, the voltage, the signal which is given to the LED transmitter or receiver is always positive, but I am doing an analysis for a signal which may have both positive and negative, but the analysis will not change our concept of VLC modulation. But for a better understanding, I am just using typical M-ary PAM system. So a PAM system is basically you have different amplitudes. For example, if you have a 4 PAM system, so for example, this is represented at 0, 0, and this amplitude is for 0, 1, and this may be for say 1, 0, and this may be for 1, 1. So there are different levels. So this is a case of 4 PAM system. And this I can use a constellation diagram to analyze the BER. So basically, if I change this system in the constellation form, it will be something like this. you have this point here, then you have one point here, you have one point here, you have one point here. And all of these, they represent either 0, 0, 0, 1, or 1, 0, or 1, 1. So we will try to calculate for a generic system, which is M-ary PAM system. So let me draw the constellation of a M-ary PAM system. It will be, so say this is 0, and say this is delta, which is away, delta point of, delta distance away, and this is say minus delta. So this whole thing between two constellation points, the spacing is 2 delta. The next will be at 3 delta. So this spacing, if you see, is again 2 delta. Similarly, I can see on the negative side, again I want to make it clear that for VLC system you require a positive signal only, but this is for understanding of M-ary PAM, so which is both valid for system which is bipolar as well as unipolar. So we can change this coordinate system to make it appropriate for unipolar system as well. So 2 delta, and this is this will be minus 3 delta. So again the spacing is 2 delta. So I can go on, and my last one will be 2m minus 1 delta. So this is the last point. And on this side, so let me put dash here. So this is 3 delta. And similarly, last point here will be minus 2m minus 1 delta. So this is a typical M-ary PAM system. This is the last point here, 2m minus 1 delta. So as you see here, SI is 2 plus I delta, where I goes from m minus 1 to 0. So as you see, I is equal to 0, this becomes plus minus 2 delta, which is shown here, plus minus 2 delta. And so on and so forth. And the last point is m minus 1. And this is written here as 2m minus 1 over delta. So if you see this M-ary PAM is actually corresponding to B number of bits. So where B can be written as log 2 of 2m, or m is equal to 2b minus 1. So for example, 2m is say 8, and then b will be actually 3. And this will be, there will be 8 levels. So this is starting from 0, and this will be say delta, this will be 3 delta, and this will be 5 delta, and 7 delta. Similarly, on this side you have minus delta, minus 3 delta, minus 5 delta, and minus 7 delta. And this can correspond from all 000 to 001. So all ones. So this will have from 000 to 111s. So this is how it can be represented for a system where 2m is 8, and so number of bits will be 3, and you can calculate from here as well, from this formula. So now let us try to calculate the BER for such a system. So the average symbol power, if I want to calculate the average symbol power, because each will have different power levels. So the average symbol power will be given by 1 by m. There is a total number of levels. Summation k is equal to 0, m minus 1 to k plus 1 whole square delta square. So this is the average powers. For example, if k is equal to 0, so this becomes delta square. So that is a power in the system. So on and so forth. K is equal to 1 and m minus 1, and it is divided by m, which is I is the total number of levels in a PAM signal are m. So this is the average power. So this is, you can write as average power or P. This is average symbol power. And this can be expanded here. So del square by m can come out. And this is 2k plus 1 has been expanded here. And further simplifying, this becomes del square by m and these quantities which are there in the bracket. And rearranging some of the terms, it can give a expression like this: del square divided by 3m into 4m cube minus m. So this m can be taken common, this m can be cancelled, and you are left with del square by 3, where I have used m as 2b minus 1 because b is nothing but log 2 of 2m. So putting this value of m here, and then we get 2 raised to the power 2b minus 1. So this is in terms of number of bits. And from here I can calculate the delta, which actually decides what is my power. So delta will be root 3p 4m square minus 1 for a M-ary PPM system.